Okay, so today we're going to be talking about understanding scientific research. If you don't want to follow this video, that's perfectly fine. There's another link to just look at the Google Slides without any of my voiceover. So just go ahead and click on that under Google Classroom. All right, so what is science? Really, you have to start with what science is not. So it's not, if you're thinking about a metaphor, it's not a massive jigsaw puzzle. In reality, when you finish a jigsaw puzzle, it only gives you kind of one picture, one look, one viewpoint. You can't really, unless you're cutting pieces with differently and trying to piece them together, that's the only way you can change a jigsaw puzzle. Science is always evolving. It's pretty much like more like a lump of silly putty or Play-Doh than it is a jigsaw puzzle. It's about predictability. So science today allows you to predict certain things about the world around us. Things like what time will it get when it's dark, and what time will it get dark today, and what will happen if I stick my tongue to a flagpole when the outside temperature is below freezing. We all know that your tongue will probably stick. All right, so how to think like a scientist. Big things to think about. You want to be curious, be skeptical, and be flexible. So being curious is just asking questions, all right? When you're a little kid, you might want to know, why is the sky blue, okay? Being skeptical. Well, if someone tells you the answer, well, it's because it's just blue, you got to kind of think, well, there might be a better answer than that. And then being flexible is, even if you find one explanation, keep looking. So research never ends, observations never stop. So be a good scientist. Keep looking, keep exploring. All right, so this is a scientific method. We're talking about 4 different pieces of the scientific method. The first is observation. So you want to do careful watching of something around us in the environment. You're looking at animals or in ourselves, and you want to look at it in an objective way. So objective measurements are quantitative, or something that you can take measurements. So how many times does your dog drink water a day? Okay, you observe that. That's quantifiable. And again, objective measurements, you want to use standard units and equipment so that someone else using the same units or equipment could measure and get the same result. So when you're building, or if you ever are going to build an experiment, you want to make sure you have quantifiable objectives, to where if you were to do one study and someone else to do the same thing, you get the same results every single time. The more quantifiable a value is, the more value it has. So it sometimes rains when the barometer reads 29.3 millimeters of mercury is better than saying it sometimes rains when my knee hurts. Okay, so you can't objectively see that in every single person, right? So not everyone's knee hurts when it rains out. Okay. The next idea is hypothesis. So it's an educated guess explaining what you are observing or how to change what you are observing. An example of a good hypothesis is you observed plant grow faster after you gave plant food, and your hypothesis could be plant food stimulates houseplants to grow, right? So hypothesis could just be an observation or some form of idea that you have, and then moving forward, when you're designing the experiment, you're going to try to answer that question. Okay. All right, the third idea is experiment. So you're testing your hypothesis. You want to design and carry out your experiment. Typically, you're going to split into the least amount of groups is 2. You have experimental and control. Experimental get plant food, control does not get plant food. All other variables stay the same. So the measurements that you choose to record should be repeatable by someone else, as well as relevant as a predictor. So what that means is repeatable is that the next person knows what you're using. So you have to be very thorough in what kinds of measurements you're taking, how you're taking measurements. Most of you guys don't know what a goniometer is, but what it is it's basically a tool that's used to assess the degrees of range of motion in a joint, okay? So you're going to put it up to a joint line, and you're going to make them either bend their knee, whether you're, say you're doing the knee, okay? So you're going to put the measurement tool on the side of the knee. Now it's very specific on where you need to put that, because putting it on a certain landmark, one person might put it on one landmark and another person might put it on others. So when you're designing your experiment, you have to be pretty thorough on what you're doing. So that's just talking about getting measurements right. And the next part is it's relevant to as a predictor, meaning that it's something that you can see is going to answer the question. So for instance, with our last question about plant food, you're not going to measure something like I talked to my plant that day and it grew. Okay, that's too many other measurements and too many other variables that could change the outcome of your hypothesis or what your idea was. Okay. Gathering data. So you want to make sure you gather enough data. Example is like when you start out the experiment, you should take a baseline and then take measurable data at intervals and use statistics to calculate the results. So as you move forward, you can see the significant difference between what has changed through the experiment, if anything. And the final part of the 4 ideas is a conclusion. So a conclusion is a judgment made on the basis of your experiment. You're basically answering whether your hypothesis in the beginning was right or wrong. 2 things I want to talk about today are correlation and cause and effect. So correlation, that's when 2 things that tend to happen together. So every time I go ice skating, A, I get cold, B, I bruise my bottom. All right, so I know that both of these happen when I go ice skating, but I don't know if one causes the other. So what I mean is, so every time I go ice skating, I get cold. All right, so does me going ice skating cause me to get cold? Maybe. The next part is when I go ice skating, I bruise my bottom. So is that a cause? Like, does that happen every single time? When you go ice skating, do you always get cold? When you go ice skating, do you always bruise your bottom? That's not necessarily true, right? So the next part is saying cause and effect. So cause and effect is one thing or event that actually causes the other to happen. So for instance, every time I go ice skating, I fall down and bruise my bottom, right? So I know that if I prevent the second one from happening, I can conclude that A causes B. Does that make sense? So you have to think about that moving forward. All right. Cause and effect means that one causes the next thing. I fall down on my bum, I bruise my bottom. All right. Not every time that you go to ice skating do you fall down. Okay. Next part. So why even bother with science? Okay. Through evolution, it has always benefited animals to be able to predict things around them, and not just animals, humans. Okay, we are technically a form of animal. So, for instance, like if a deer smells a wolf, it can predict danger and run the other way. Right? If a ground squirrel feels a temperature drop, it can predict winter is coming and prepare to hibernate. And for instance, in humans, there are warning signs in our lives that predict tax raises, spoiled food, etc., and we alter our behaviors based on the predictions we make. So knowing about spoiled food, what happens to milk when it starts to spoil? Right? It starts getting chunky, right? So when we start seeing that, or for instance, most things when they start to spoil, they get an odor to them, and it's usually a foul odor. So for us, we've learned and interpreted over the years of us evolving that we should not eat something that smells bad, right? And the other thing is when you're a baby and a kid growing up, that's why your palate is, you want sweeter things, okay? If you didn't know, most bitter food or most bitter tasting things are actually poisonous in some degree. I can't say everything that's bitter is poisonous, but the idea is through evolution, kids don't want to eat things that are bitter because it's almost like us thinking like, well, that's not good for us. We should not be eating something bitter like that. And as we start developing, we become more immune, obviously with age, And so over the years, our bitter taste buds kind of go away, or our bitter, foul tasting buds go away. So now we can actually eat something that might taste bitter and not hate it. So science is just a way of making predictions. Using medication X will clear up Z. Wearing a seatbelt will prevent you from flying when through the window in a car accident. And depletion of the Earth's ozone layer may increase the risk of cancer. Just some ideas. All right, so these are some great truths that have been thought at one point throughout the century. Okay, centuries, I should say. So in 4000 BC, the moon is eaten once each month by a large invisible beast. All right. Now you might be thinking to yourself, that's not true, right? It's usually the shadow of the Earth on the moon that you can't see the moon, right? So 1400 AD, diseases are caused by evil spirits that inhabit the body. Is that true? Not necessarily true, right? We're talking about pathogens. We're not talking about evil spirits. So there's not a demon in my body when I have the flu. It's a virus. 1500, flies develop spontaneously from rotten meat. Now, we know that doesn't happen. Typically, it takes a fly to lay its eggs, and then the larvae actually eat the meat as they start growing and getting bigger, and that's why we get flies. In 1600, the brain pumps fluid into the muscles, making them bulge and contract. Now, we know instead it's nothing about fluid. It has to do with neurosignals. Okay. In 1800, Tyrannosaurus rex walked vertically and dragged its tail. We know that's not true. If any of you guys have seen Jurassic Park, they usually lean forward, okay, and their hands and their tail kind of leaves some form of balance, okay, but they don't walk straight and vertical. In 1850, the planet Mars is covered with canals that only could be made by intelligent life. That's not true. We know that Mars at one point had its own oceans, and so that's basically like the floor of the ocean or water. In 1900, the Apatosaurus and Brontosaurus are two different dinosaurs. We later found out that they're the same. 1970, Saturn is the only planet with rings around it. That is not true. I think it's Uranus is the other one. I wish I was an astronomy teacher, but I think it's one of those. In 1980, eating eggs makes your cholesterol levels rise. That's not true. It happens with some people, but not everybody. In 1985, pandas are bears. Pandas actually are more closely related to raccoons than they are bears, according to the genetic kind of makeup of them. So in 1990, tadpoles eat plants and frogs eat meat. What they have found in the future is that, and they found out since, is that there are some frogs who do eat plants. In 1995, the Human Genome Project begins and estimates that human chromosomes carry more than 100,000 genes. It actually does about 6 million genes. Okay. And then in 1999, the year 2000 problem, aka Y2K, or the Millennium Bug, was predicted to make some computers unable to handle the date change at the turn of the century. None of you guys were alive at that time, but living through it, it was my second year of high school, so I was a sophomore. And they were freaking out that basically if you had a desktop computer, which was the thing back then, we didn't really have laptops. If you had a desktop computer, you would have to unplug it from your wall in your house and make sure everything shut down and everything was saved on like a floppy disk or something. And because they were afraid if your computer was plugged in and turned on at the kind of stroke of midnight when it went to 2020, then your computer would act as a small bomb and blow up in your house. What ended up happening was none of that happened. Everything went over completely fine. The stock market did not crash. People were able to handle their bank accounts with no issues. And really, technology did not harm us. So reality kind of struck with everyone the next day when people turned on their computers and they were all fine the next day. So, all right. So that's kind of talking about just scientific research and the basics. After this, please take the quiz that's associated. It's Understanding Science Scientific Research quiz. I think it's about 5 questions, and then you are done for the day.